Very good. So now, let's take a look at the far field. So to compute what's happening in the far field, once again, we are considering all of our, let's try to make that more of a straight line, right? We are considering along our x-axis. Here will be the x equals 0 point. We are considering all of our Huygens wavelets, right? And now, what we're going to do, I won't sketch all of them, but what we're going to do is compute then the intensities, the brightnesses that we can expect as now the waves propagate out from here and then impinge upon my photoplate, eventually out at some angle theta, and we want to calculate then what all of these intensities will be as a function of this angle theta. Now, the basic idea here is that the brightness then that we get at these different angles theta, which implicitly are telling us about the x momenta of the particles, their distribution of that momenta once they've passed through my filter. That brightness we get by brightnesses are always a complex magnitude squared, right? We're adding up our phasors here, of a superposition of what happens to these little Huygens wavelets when I add all of them up and as each one then propagates out to the particular point where I'm going to land on my plate. So I have to add up a superposition of all of these little wavelets. So that means there's going to be a sum, or in this case actually an integral, over all of x, because I have a whole continuum distribution of these point-like sources. And each of those sources starts out with a certain amplitude and phase, which we've combined into this complex amplitude, which we call the wave function psi. And now, for each of these individual contributions, we have to figure out what else happens to it on its way to the final observation point. So on its way out here, first, this point source, the intensity of it, or the brightness, begins to dim with distance, like any normal point source does. So there's a factor here that describes a decay in the amplitude with distance as those waves spread out. And that factor actually varies as, and this is again one of these proportionalities, that factor always varies as 1 over r. The reason is that when we square it, we will find the brightness of these point-like sources drops off like 1 over r squared, which is the normal behavior for the drop down in the brightness. And one very important point. Now you can see, by the way, why I chose to make my second photoplate a circle at constant radius r, so that this really will just become a constant I can pull out of my integral, and it just won't affect my basic proportionality relationship in any way whatsoever. The next thing, though, that we have to take into account is what happens not only to the amplitude of this little wave as it propagates outward, but to the phase of the wave. Because, once again, on their way out here to the final point, and remember, this final point is very far away. I should draw like a broken line here. This is far out, right? Because it's so far out, any of my little Huygens wavelets, say this one up here at distance x, I'm going to be focusing on this one, right? They all, to reach this point, are traveling outward at the same angle theta, right? So we have this second path along a essentially parallel path. And you will notice that once again, there's a difference in the phase. When I drop my perpendicular, so that I know this distance and this distance are the same, I have this little extra distance. But I want you to notice the excess distance is different now, right? It's the point at the origin that has to travel further. As I move further up in x, I actually have less phase in order to reach the final destination. So there's an additional phase factor we have to consider here. I'll call it, and we can take it into account as a complex phase factor, e to the I phi prime of x, I will call it, because it's the phases now I'm accounting for as we travel out into the far field on the other side of my filter. This is just the generic formula for computing a brightness. In the far field, far away here on my plate. The big question is, okay, what do I use now for this function phi prime, this second phase? Now, as we've just commented, the relative phase that we're computing now is a little bit different in that the relative phase between the origin point and my point is such that as x increases, I have a decrease in the phase. So I count for that with the minus sign. There's going to be less phase buildup. And the amount of the buildup we compute in the same way. It's 2 pi so that we can have things in radians, divided by my wavelength lambda so I can count the number of waves. And now I need to account for this distance. But the geometry again is very similar, right? If this angle here is theta, then that makes this angle the complement of theta. And then this angle up in here actually would equal my angle theta, and you can see then my excess distance is opposite my angle theta. My hypotenuse is x, so it'll just be x times the sine of theta. And from this portion on, it should look very familiar to you from how we analyze the incoming waves, right? Not to belabor the point, the wavelength then will be the momentum of the particles divided by h bar. This momentum is constant and set, of course, by that of my source. I can simplify this now rather quickly. The lambda is not p over h. I'm sorry, guys. It's h divided by p, right? So the momentum ends up on top. So I'll put it up there. It then can combine with the sine of theta. Very good. Once again, I still have my factor of x that I can write on the outside. And again, also, don't forget, now I have a minus sign, but again, also, there's h in the denominator with a 2 pi in the numerator, so this is just divided by h bar. Again, same story. P times sine theta, this is actually the outgoing momentum that we're trying to measure. That is the momentum that the particle has as it passes through my filter. This is the thing whose distribution we're actually trying to determine. And my phase factor enters just like that momentum, but divided by h bar. So once again, I see momentum, I'm thinking, oh, that's just like a wave vector. And h bar is my conversion factor. So this actually does give me a standard phase looking form. It's going to be minus now what I will call k times x. And I will call it k without any subscripts because the x component of the momentum, which is actually the only momentum we're concerned about here, right? We're thinking about just motion in the x direction, one-dimensional quantum mechanics we're doing right now. That momentum I'm defining as h bar times k, and as I've said, wave vector k we should always think of as the same thing as momentum. So I will just call this k. The other k was k naught because that was the incoming fixed momentum in the x direction coming from the source where they all come in at the same angle, but they don't all emerge at the same angle. So this k is a variable tied directly to the momentum that I'm trying to measure. So now we can put this all together. If I want to calculate something like the probability distribution for the momentum in the x direction, right? Which I know is essentially the same thing as h bar times k. It's the same thing as determining k. That probability distribution would be proportional to, related to, right, this brightness that I measure at the corresponding angle theta, right? Where px is, of course, p times sine of theta, right? And that brightness is a function of theta. I know how to compute this way. That is proportional to, right, the square of the integral of psi of x, right? Now, I have my phase factor I should write down, and that's e, and my phi prime of x, right? Where is e phi prime of x? Is just minus kx, so it's e to the minus I kx. And now there's this divide by r. But as we had commented, that is a constant. So I can pull it out of my integral. I can pull it out of my square. And so it's just an overall constant I can combine with the other proportionality constants. So I can just leave this as a direct proportion. And then the only remaining piece is to finish off my integral dx. And if you want to be technical about it, of course, I am getting Huygens wavelets from all different positions x, so I have to integrate from minus infinity to infinity. So this gives me then the prescription for calculating the probability in the x direction.